So far we have been talking about Grover's search algorithm, and now I intend to switch over and discuss another major algorithm which is known as source factorization algorithm. The reason behind discussing this algorithm is this is one problem, as we will see later, requires exponential time in classical computation, but the quantum part of it can be completed in polynomial time. Now we will discuss it in detail as we go along in the next 3 or 4 lectures, but before I can introduce you to the methods of source algorithm, I need to introduce some or acquaint you with some mathematical preliminaries. And today I will start with one of them, and that is known as quantum Fourier transform. The quantum Fourier transform, if you all remember what is Fourier transform. Now normally in physics that we have, or even in mathematics, when we have been discussing various types of transforms, for example Laplace transform or Fourier transform, etc., we have been doing it on a continuous variable. Now in dealing with our quantum information and computation, we are restricted to use discrete variables, and so what we are going to do now is to first introduce the concept, general concept of a discrete integral transform, and then having done that, we will define a specific kernel for the quantum Fourier transform. Remember what is a kernel. Now, even in our standard definition of Fourier transform with or real variables, our definition was, for example, if I had a function of x, fx, then we said that we define its Fourier transform as some function of k, fk, equal to e to the power ikx integrated over e to the power ikx fx from minus infinity to plus infinity. And for example, if you wanted a Laplace transform, then instead of e to the power ikx, you would define it as e to the power minus lambda x, where lambda is real. So this thing which multiplies the original function and then we integrate out, that's what is known as the kernel of the transform. If you go to the slide, what is the reason why we need it? So they are used in many things, the Fourier transforms or Laplace transforms, but typically their job has been to convert a mathematical problem to a relatively simple problem. For example, you could be using it to solve differential equation, and by taking a Fourier transform, you could convert this to an algebraic equation, which presumably is easier to solve. And then of course, since I need the original solution, I apply an inverse transform so that I can get back the solution that I want. So let me first talk about a general discrete integral transform, in short DIT. So let small n belong to the set of natural numbers, and I will take Sn to be a set of numbers which has 2 to the power n integers. So this is a set consisting of 0, 1, 2, etc., etc., up to 2 to the power n minus 1. Now let me take 2 discrete variables belonging to this set. Let me call one of them x and the other one y, each one of which can take these values 0, 1, 2, 2 to the power n minus 1. So x, y, which belong to my set Sn. Now I define kxy as a bivariate function which is in general complex, as a function of x and y. The difference between what we are talking about here and what we are accustomed to talking about in our real variable theory or complex variable theory is that these arguments here can only take discrete values, but kxy could be any continuous function of these discrete variables as well. So I am not saying k has to be necessarily discrete. Now let me define using these the discrete integral transform of a function f sub of f. Now this is a function of the discrete variables. So f is a function of x, which is, let us say, a discrete variable. Then f tilde of y, which is the dit of the function f(x), is given by a sum instead of the integral with which we are familiar, x equal to 0 to n minus 1, the complete set, k yx, this is that bivariate kernel I talked about. So this is the kernel times f of x. Now notice, since x and y are both discrete, this is actually a set of simultaneous equations. What we will do is this, that we will say that f of x and f tilde of y, they are both column vectors, and then of course this becomes just a matrix equation. This the equation that I wrote down, that becomes this is the matrix equation. Now let us suppose this kernel is invertible. My general definition would simply require it is invertible, but suppose I make an additional demand which is not required for this definition, but is required when I talk about the kernel corresponding to the quantum computation. Supposing this k happens to be unitary. So if k is unitary, then I know that k dagger is defined, and I can then talk about an inverse transformation, that is starting from f tilde of y equal to 0 to n minus 1 again, and k dagger of xy f tilde of y. So this is my integral transform, and I get back the function by applying an inverse integral transform. Now having discussed this, let me now extend this concept to a Hilbert space of n qubits, C to n, that we have been talking about. Now suppose by vector x I indicated a n qubit basis. Well, it does not have to be basis, but let us say n qubit vector, xn minus 1, xn minus 2, etc. up to x0, where each of these numbers, as we have seen, xi takes the value 0 or 1. Then I would apply a unitary operator ux, u on x. Now by completeness, I can write this as y equal to 0 to n minus 1. I introduce the identity operator here. So this is my identity, and then of course ux. Now you realize that this way of writing, I have essentially written this as a matrix element of the unitary operator in my basis states. So this is nothing but sum over y equal to 0 to n minus 1 u yx, which is the matrix element. So this is this quantity's definition, acting on a vector y. Now what I am going to do is this. I am going to take this statement for the way an unitary operator works, and I am going to ask to compare this with my definition of the Fourier transform or integral transform. So this was equal to x equal to 0 to n minus 1 k yx x. So you notice, other than from some role change of x and y, these two equations are essentially the same, provided if I identify U to be a unitary matrix which gives me this. If U acting on x gives me sum over y equal to 0 to n minus 1 kxy y, then I can make a statement that this operator U, the unitary operator U, it computes the discrete integral transform of the basis states, the states that we have, n qubit states. Now that's not all. The advantage that we have now is that because we follow linear algebra and because of the quantum parallelism, the DIT of any function or any linear combination can be computed in one go. And to look at how it does that, U acting on sum over x fxx. What does it do? So this is, by linearity, I have sum over x fx U acting on x, and just now we said U acting on x is, so I have a sum over x already fx, and U acting on x was identified with kyx. Actually it should have been xy y. I can, because these are finite sum, I can without problem interchange them, and so therefore I have this thing x k xy fx y. But if you recall, this was precisely my definition of the integral transform. So this is equal to sum over y of f tilde of y y. So with that, I have defined what is an integral transform, and now I specialize it to the case of a quantum Fourier transform, which is simply extending this concept to a very special case where the kernel looks very similar to the way we had taken for the case of normal Fourier transform. So what we do is this, that quantum Fourier transform, frequently written as QFT, there my kernel kxy will be taken to be 1 over square root of n e to the power 2 pi I xy divided by n. You notice that e to the power 2 pi I by n is nothing but nth root of unity, and in usual complex variables we have been representing this as an omega n. So therefore this is 1 over square root of n omega n raised to the power xy. one thing I want to point out, that in this case, the product xy is a normal product, usual decimal product. What do I mean by that? Because frequently we have been talking about bitwise product. Now in this case, we take x and y which have a decimal representation, in the sense, for example, if you take 101, now then I know that 101 stands for a decimal number 5. So here the x and y are usual decimal numbers and kxy is taken to represent that. So not bitwise multiplication. I will make it further emphasize it, not bitwise. Let me give you an example of this. Let me take n is equal to 1 qubit, so that capital N is equal to 2. I am in 2-dimensional space. By definition, my kxy is 1 over square root of n, which is 1 over square root of 2, e to the power 2 pi I xy divided by 2, because that was n. Now remember, e to the power 2 pi I by 2, which is e to the power pi I, which is equal to simply e to the power pi is minus 1. So therefore this is cos pi plus I sin phi. So it is minus 1. So therefore this is, I know what is this value. So let us look at this minus 1 to the power xy. This is by De Moivre's theorem, e to the power pi I equal to cos pi plus I sin pi, sin pi is 0, so that is the way it is. So what is this matrix K? Remember that my x and y in this case can take values 0 and 1. So if I write a matrix, this is 1 over square root of 2, x equal to 0, y equal to 0, so it is 1, 1, 1 and then minus 1. Recall this matrix. This was the matrix which corresponded to a Hadamard gate. So this was Hadamard matrix. In other words, the Hadamard gate implements quantum Fourier transform in C2. So QFT in C2 is implemented by Hadamard gate. And so therefore, if you want to find out what is the QFT of alpha 0 plus beta 1, you could simply do it by means of whatever you have said just now. And you can see that 0 becomes 0 plus 1 by square root of 2, 1 becomes 0 minus 1 by square root of 2. Let me continue with this example. Let me give the first non-trivial example, n is equal to 2, which means capital N is equal to 4. So that my x and y belong to the set 0, 1, 2, 3. Now I have got omega 2, n is equal to 2, which is e to the power 2 pi I divided by capital N, which is equal to 4, which is e to the power pi I by 2. So this is cos pi by 2, which is 0, plus I sin pi by 2, so this is equal to I. You can write down the matrix K. Kxy has elements given by I to the power xy, x and y running like this, and show that the matrix K is given by this 1, 1, 1, 1, 1 I minus 1 minus I, 1 minus 1, 1 minus 1, 1 minus I minus 1 I. Summarizing the results, the first thing is to realize that K is unitary. Let's see why. The slide shows the proof. So firstly, you realize that this was my definition of a Fourier transform, and this is the definition of the inverse Fourier transform. So that what is the matrix element of K dagger in the states x and y? So x, K dagger, y. Now I evaluate it by the following. I will introduce a complete set, that is resolution of identity, z equal to 0 to n minus 1. I have x, k, z, k dagger, y, and since I know these matrix elements by our definition of Fourier transform, so this is sum over z equal to 0 to n minus 1, k xz, k dagger of zy, and you can immediately write down that this is equal to z equal to 0 to n minus 1 of e to the power 2 pi I z x minus y. Now because of the fact that these are finite geometric terms, finite geometric sum, I can easily compute this sum. But before I do that, I have to realize that this term x should not be equal to y. Now if x is not equal to y, so that this is not equal to 0, then my common ratio is e to the power 2 pi I times whatever that quantity is. So that my sum will then be e to the power 2 pi I x minus y minus 1 divided by e to the power 2 pi I x minus y by n minus 1. Since x is not equal to y, the denominator is not equal to 0, but the numerator becomes 0, so therefore this sum becomes 0. But on the other hand, if x happens to be equal to y, I had, while writing this down, I had forgotten a factor 1 over square root of n, so I need to introduce that 1 over square root of n twice, so therefore 1 over n is there. Now, so this is still equal to 0, but if I have x is equal to y, note that this term becomes 0. Because if it becomes 0, then my e to the power 0 is equal to 1 all over. So I have got n number of terms, each one of them equal to 1. So therefore, I get n as a sum, and I have a 1 over n which gives me 1. So therefore, if x is not equal to y, I get 0. If x is equal to y, I get 1. So therefore, I will say that k dagger matrix element x y is simply given by the Kronecker delta of x with y. So what we have done today is to extend our concept of Fourier transform for real and complex variables, continuous variables that we had learnt in physics and mathematics, to the case where my variables are discrete. Because of the fact that we deal with sums rather than integration, getting explicit representation of the kernel is fairly easy, at least for those cases where the n value is small. And we had seen that for n is equal to 2 in space C2, my quantum Fourier transform is equivalent to doing a Hadamard gate operation. We will see that quantum Fourier transform has a significant role to play in our discussion of source algorithm. And as an exercise, I will be giving you more examples of quantum Fourier transform in a separate session.